So we're going to go through the Unit 5 Notes Part 3. This is going to cover formal charge, bond length, bond order, and bond energy. Formal charge is a hypothetical charge, so it's just something that's made up in order to find the most stable organization of the atoms, or in other words, what's going to be the actual shape of the atoms around the central atom. So to get this, you're going to add up all the electrons around the atom, with bonds counting as one electron for each atom involved in the bond, and subtract the number of valence electrons. So the best way to do this is do an example. So really you're just continuing on the same thing. Carbon has 4 valence electrons, oxygen has 6, bromine has 7 times 2 is 14, so when we add all those up, that's 24 total electrons. You're still following the same process of carbon is the central atom, oxygen is single bonded as we do a skeleton structure, bromine here. Distribute electrons around the outer side, around the outside, so we got 2, 4, 6, so you got 8 around this bromine, 8 around this bromine, so that's 16, 18 here, 19, 20, 21, 22, and hopefully what you can see is you could put 2 more on the oxygen, but you're going to end up with only 6 electrons around the carbon. So really what's going to end up happening is you're going to get a double bond. So now to do formal charge, you look at each atom individually. Oxygen has 1, 2, 3, 4, the lone pairs, 5, 6. Each bond counts as 1 for the oxygen. So there are 6 electrons around oxygen currently, minus the number of valence electrons. So what number tall group is it in on the periodic table, which is 6. And it has a formal charge of 0. Carbon has 1, 2, 3, 4 bonds around it, so that each bond counts as 1 electron for it, so 4 minus 4 is 0. Bromine has 1, 2, 3, 4, 5, 6 lone electrons and 1 in a bond, so 7 minus its valence electrons, which is 7, which is 0. And this one's the exact same thing, so 7 minus 7 is 0. If you notice now, the formal charge on each of these is 0, which means it's as stable as it can be. In other words, the amount of electrons around each atom are equal to the number of valence electrons, which is when it's going to be at its most stable. So, if there's more than one structure possible, we can determine it based on the following rules. 1, the correct structure has the lowest magnitude of formal charges. In other words, like we just showed, if everything's 0, that's going to be the most stable way to do it. And 2, if 2 structures have the same formal charge, so you're seeing the same charges no matter how you arrange it, the one with the negative formal charge on the most electronegative atom is correct. Remember that the most electronegative atom would be found in the top right-hand part of the periodic table. So when we're looking at something like SOF2 here, F is the most electronegative atom, so if we're going to come up with a structure for this, we want any negative formal charge to be on F, which would be the most electronegative atom. So SOF2, just following our rules, adding up the valence electrons first. This is 6, this is 6, and this is 2 times 7, which is 14. So we're going to have a total of 26 electrons to play with for SOF2. So you're going to put S, F. This is going to look a lot like the last one that we just did, F, and I'm going to kind of cheat here a little bit since I know what this structure looks like, and we're going to put there. And then you're going to have O, and we've used 16 for the fluorines over here, that's 18, 19, 20, 21, 22, 23, 24, and then any left over in the middle, so there's 26, okay? The other thing that you can notice here is because sulfur is one of the exceptions to the octet rule, you could also do this as a double bond. So I'm just going to redraw that out real quick. Oxygen with its lone pairs, you could do a double bond to S, still have 2 there, F, and an F. So, the way you determine which one's the correct thing is to do the formal charge. Here, oxygen has 7 around it, minus 6 that it normally would have, so that's plus 1. Here, sulfur has 1, 2, 3 bonds, so 3, plus a lone pair, so 5, minus 6 is negative 1. Each fluorine has 7 minus the 7 it should have, so 0, so the fluorines are actually pretty stable. Now if we look over here, oxygen has 1, 2, 3, 4 lone electrons plus 2 bonds, so 6 minus 6, which is 0. Sulfur has 4 bonds plus a lone pair, so 6 minus 6, which is 0. And the fluorines still are 7 minus 7, which is 0, and 7 minus 7, which is 0. So if we're asked which structure is right, it's the one on the right because all the formal charges are 0, versus the one on the left where you have a positive and a negative charge on oxygen and sulfur. Down here for bond length and bond order, bond length is the distance between nuclei and a bond. It's found by adding the two radii together. It says page 360. It's actually around page 310 on your book, in your book. So you're going to go and look things up. It says, what is the bond length of OH? So all you're going to do is go find the radii of each element. Oxygen has a radii of 66 picometers, and hydrogen has 37 picometers. So when you go look those up in your book to get those numbers, you're going to end up with a bond length of 103 picometers. Bond order is the number of pairs of electrons in a bond. The higher the order, the shorter the bond. So it says which CO bond would be the shortest in formic acid. So if you draw out formic acid, so it's C surrounded by O's and H's, I'm going to save you a little bit of time, but this is what it looks like when you draw out formic acid. We haven't done organic, so you don't worry too much about why that is the way it is, but that's what formic acid looks like. It's going to ask which CO bond would be the shortest, and in this case the shorter one is going to be here. And if you look them up, there's a table in your book around page 310 as well. That's 123, a CO double bond, and this is 136 picometers for a single bond. The reason why it's shorter is you have more orbitals overlapping. So in order to have more overlapping and share more electrons, the nuclei need to get closer together. The final thing is the bond energy. That is the correct value. The values are actually found on page 316. And all you're going to do is, just like you did with the delta H's, where you use some of the products minus some of the reactants, we're going to do the same thing here with bonds. So in order to do this, you got to kind of actually draw out the different molecules. So C2H4, if we follow our rules, would look like this. Plus O2, which looks like this. We don't really care about extra electrons. All we care about is bonds in this case. So then we're forming that, and water looks like this. Okay? So when we do this, in order to break a bond, you need to put energy in. So the energy in will break the bond, and then when we form energy, we tend to lose that energy back out. The energy that goes in to break the bond is lost as the bond reforms, a new bond reforms and comes back out. So all the bond energies in your book are going to be positive because that's the amount needed to go in and break the values. And everything that comes out is negative. So usually the way you do this is add up the value of the bonds that are broken, so all the reactants, and subtract the sum of the products, which is all the stuff that was formed. So what you're going to do is you're going to go to page 316 and you're going to look up all the values. A CH bond has a value of 441 kilojoules. A C double bond has a value of 602 kilojoules. And an OO double bond is 494 kilojoules. A CO double bond is 799. And an HO single bond is 459. So then what you're going to do is add up the values. So in C2H4 there are 4 CH single bonds, so 4 times the energy for 1. Plus there's 1 CC double bond, so plus 602. Plus there are 3 oxygens, each with 1 OO double bond at 494. So there's the sum of all the energy that went in to break bonds. Now we subtract the sum of what came out. There are 2 CO2s, and each CO2 has 2 double bonds. So there are 4 times 799 plus 4, because there are 2 waters, times 459, because each water has 2 single bonds. So when you do this, you end up finding that the value is negative 1304 kilojoules. What does that tell us? It tells us that we lost energy during this reaction, which means this is an exothermic reaction. It's the exact same thing you were doing with delta H when you were looking up the values and solving for products minus reactants. The only difference here is we're doing it with the energy from the bond. So we're actually coming up with the value of delta H based on how much energy is needed to break these bonds or form new bonds. Look on the website now and you can find the homework for tonight, and good luck.